Here we are. This set of notes is about a topic of continuity. And this is going to be important because continuity is going to be a condition for a lot of the theorems and properties we talk about to be true. In order for a function to have certain things exist or for certain things to be true about them, one of the things that we start to talk about is that the function has to be continuous. And continuous, one way that I think about it is continuous means connected. And that means there's no interruption in the graph at x equals c. So if the function is continuous at a point, it means that there's no interruptions in the graph. What do I mean by interruptions? Well, a hole in the graph would be an interruption in the graph because there's not a point there. If there's some kind of jump in the graph, or if there's some kind of gap, an asymptote would make something not continuous. Another way I have to describe it is that you should be able to, if the function is continuous in a certain interval, then you should be able to draw the entire interval without having to pick up the marker. As soon as you have to pick up the marker to maybe go down here, not continuous. So continuous is connected. It means that there's no interruption of the graph. This function is continuous everywhere between a and b. So a couple more ideas. So first off, f of c has to be defined. There can't be a hole in the graph. We can't have the function not exist at that point. The limit exists, meaning there's no jump in the graph, because if there's a jump, then the limit from the left and the limit from the right aren't the same, and so the limit doesn't exist. And then no gap, meaning that that we don't have the points suddenly it's coming together, and then it jumps up here. Right? So if we had something like, that's not continuous. I had to pick up the marker to draw this other point. So, in other words, another quick way to define continuous is that the limit as x approaches c of f of x equals f of c. In other words, the limit of the function and the actual value of the function match up. The limit goes to the same place as the actual function goes to. Some functions can be continuous over an interval, but not continuous over the entire function. So if I've got a hole in the graph, then the function's still continuous everywhere else, just not at that hole. That's where we're not continuous. If the function is not continuous, we call the point that it's points that they're not continuous points of discontinuity. Discontinuity would be places where the function isn't continuous. So here's more visuals of places where function would not be continuous. Remember, a hole usually happens if we're canceling out something on top and bottom. We talked about that when we first started talking about limits. Types of discontinuity. I just said discontinuity is a place where something's not continuous. We have two different types. We have removable and non-removable. These are basically holes and everything else, some kind of jump or asymptote or something like that. If all I did was take a point and remove it, and then maybe put it somewhere else, like up here, that's a removable discontinuity. Because all I did was I removed the point from the graph. And if I had put it back, then it would be continuous again. That's a removable discontinuity. A non-removable discontinuity means that I have to do something more to the function in order to make it continuous. Like there's an asymptote, and I would have to like get rid of the asymptote somehow, or I'd have to take this whole thing and put it down here in order for it to be continuous again. Removable just means I got rid of a point and maybe put it somewhere else. And all I'd have to do to make it continuous again is to put the point back that I removed. That's a removable discontinuity. This is non-removable. All right, graph the function, discuss the continuity of the function. So making the graph is something that we spent last week talking about. So hopefully the first thing that you did, because my assumption is that you're already starting on it here. Hopefully the first thing you're doing is factoring this bottom. X minus 2's cancel on top and bottom. So what we have here the x minus 2's canceling gives me what? What's happening at 2? If they're canceling on top and bottom, that's a hole in the graph. And then negative 2. What type of asymptote? Vertical. Where's the horizontal asymptote? It's at 0 because degree on top is less than degree on the bottom. And so if we have a hole at 2, that means 2 is removable or non-removable? It's removable. Removable would be our hole in the graph. Our vertical asymptote would be a non-removable discontinuity. Horizontal asymptote at y equals 0. And so here's what the graph looks like. Some software, it doesn't like having the holes in the graph. And so I don't know what's going on over here. What should be happening is a hole. It shouldn't be like jumping down like this, because then it would be a non-removable. This is a hole in the graph, and then we're continuing on. Here's the asymptote at negative 2. Horizontal asymptote at 0. To bring back our definition of continuity, the idea is that for the function to be continuous, I would have to fill in the hole in the graph at that point. In other words, I would need to match up and say, I'm going to fill in the hole, and I'm going to fill it in at whatever the limit of the function is. The limit of the function has to equal the value of the function. Next one. You should know how this factors already. So we have 2 and negative 2 again. So what's happening at 2 and negative 2? Vertical asymptotes, so that means what type of discontinuities? Non-removable for vertical asymptotes. So this graph looks like this. Not a hole in the graph anymore. Okay. Next example. Square root of 25 minus x squared. This is actually a graph that they like to ask questions about. They like to look at this type of graph of the square root of something minus x squared. So we're going to talk about what this graph looks like. But first, let's talk about negative 5 to positive 5. What is the problem with domain on this function? For square root, what can't we put in? We can't have square root of negative numbers, right? Can we have square root of 0? Yeah, it's 0. So we can't have the square root of 0. We cannot have the square root of negative numbers. That's why we're going from negative 5 to 5. Because as soon as we plug in something bigger than 5, or more negative than negative 5, say we plug in 6, then we get 25 minus 36, and now we have negative numbers. But if we plug in, say, 0, that's fine. Any problems between negative 5 and positive 5? Should give us either positive numbers or 0. Can we take square root of positive numbers or 0? Yes, we can. Continuous to over the closed interval from negative 5 to positive 5. What does this graph look like? Well, let me put it in a more recognizable form. I'm going to square both sides. I don't like the square root. Do we recognize that form? It is a circle. That is a circle. A circle with a radius of 5, right? Square root of 25. That's something I talked about all the way back in geometry. It's one of the last things we did in geometry was get equations of circles. And we said that this was the radius, and then we would have this hk inside of here as the center. So it's centered at 0, 0, radius is 5. Except when I take the square root, if I wanted the full circle, I would want the plus or minus. But if I had a plus or minus, then it wouldn't be a function anymore. So this is giving just the positive values, so it's going to be the top half of the circle. That's what that function looks like. And it's continuous everywhere between negative 5 and positive 5. They like this semicircle graph. You'll see it come up other times. All right. Continuity on a closed interval means that the limit from the left and the limit from the right are the same, and it's the value of the function. Right? So I wouldn't want, here's the limit. It's getting closer and closer to this point. I wouldn't want it to suddenly, the function to actually be like, oh, by the way, I'm up here instead. Just kidding. You thought I was down here. I'm up here now. That's no good. That would be a removable discontinuity. So connected, in order for it to be connected, then I need the limit to be the same as the value. Some properties of continuity. If I've got a function, or if I've got two functions, then if I take the function and multiply it by some number, then it's still continuous. If I add together continuous functions, they're going to be continuous. If I multiply together continuous functions, they're going to be continuous. If I divide continuous functions, they're going to be continuous as long as the bottom is not 0. Once the bottom is 0, then we have discontinuity. Functions that are continuous. Polynomials. So x cubed, x to the fourth, all of those different functions are continuous everywhere from negative infinity to positive infinity. Rational functions. If I take a polynomial, divide it by another polynomial, those were continuous everywhere that the bottom wasn't 0. Right? We just did those examples where the problems were -2 and +2, because that's where the bottom was 0. Everywhere else, the function was continuous. Radical functions, so everywhere in their domain, right? We can't put in, so our domain of a square root function would be 0 to infinity. Everywhere in that domain are functions continuous. We just saw that in the last example. And then our trig functions, everywhere in their domain. So if I have an asymptote, then obviously it's not continuous at that asymptote, but everywhere else it's continuous. Sine is continuous everywhere. Cosine is continuous everywhere. The other 4 are continuous everywhere that there's not an asymptote. If a function is continuous, then we can have the composition of the function also be continuous. So let's take a look at what that looks like. So if f and g satisfy the conditions, then the limit as x approaches c of a composition is the composition at that value. So let's take a look at that in action, okay? So we're going to talk about the continuity of f of g of x here. Any problems with f? Any discontinuities? No? Oh, that's 6. And it's removable or non-removable? Non-removable. Ignore the fact that I started to write removable without thinking. It's non-removable. At x equals 6. G of x, any problems with g? That's a parabola. Parabola is going to be continuous. I can draw a parabola without having to ever pick up the marker. Continuous on the interval negative infinity to positive infinity. So we're continuous everywhere. So get your guesses in now for f of g of x. Before we do it, I'll give you 30 seconds to think about how many places do you think that the function will not be continuous? And where is it going to end up being? Is the function going to be continuous? Is f of g of x going to be continuous at 6? Will I be able to plug in 6? If it will be, if it is continuous at 6, then do I just have it continuous everywhere? or is it not continuous somewhere else? Are other problems aside from 6 going to pop up? Let's look. F of g says to take g and put it into f. So here's f. Here's the structure of f. 1 over whatever we're putting in minus 6. What are we putting in? We're putting in g of x. G of x is x squared plus 5. X squared plus 5 minus 6 is x squared minus 1. And so we have issues at positive and negative 1. Are they removable or non-removable? Non-removable. Well, plug in 6. What do I get?
I didn't know since 1 over 35.
1 over 35. So now that we're used to g of f. But this cues me into I may still have discontinuities. If these were both continuous everywhere, then we'd be able to say, well, f of g is going to be continuous everywhere without even having to check it. This tells me, oh, I might need to check some points. And the bottom is the problem, so once I plug this into the bottom, then new problems start to come up. All right. One more? Yeah, we got a few minutes. Let's do our next one. Define g of 4 so that the function is continuous at x equals 4. Right now, if I plug in 4, what do I get? 0 on the bottom and 0 on the top. I have 0 over 0. So that means that the function doesn't exist there. And if the function doesn't exist there, then it's not continuous. But this is a removable discontinuity. So where do we want to put? If I took the point away, that's what happened. There's a hole in the graph. If I wanted to put it back so that it was continuous, where would I put it? Like it probably looks something like this. So if I want it to be continuous again, where do you think I'm going to put the point? How about there? That seems like a good spot for it. We're defining g of 4. We're saying, where do I put the point back? Well, I'm going to put the point back at the place where that hole is. Algebraically, how can I find where that point is? Right, and that's the process of finding the limit. Because we want g of 4. We want g of 4 to equal the limit as x approaches 4 of g of x. That's our definition of continuity. That's what we want to happen for continuous. So what is the limit as x approaches 4? Let's look. 4 of x squared minus 16 is x plus 4 times x minus 4. And then on the bottom, how does this one factor? Now we can cancel on top and bottom. X plus 4 on the top. x plus 1 on the bottom. Oh, now we can plug in 4. Remember, keep the limit notation until you plug in the number. Then you can take it away. 4 and 4 is 8. 4 and 1 is 5. That means we want g of 4 to be 8 over 5. That's where this hole in the graph is. So if we put the point there, it'll be continuous again. That's why it's a removable discontinuity. Because all I did was remove that point at 8/5. This function would be continuous at 4. There'd be no problem. I could plug it in and get out 8 over 5. Okay? Questions on any of that? Tomorrow, what we're going to look at is our first theorem about continuity. Our first theorem about continuity that's going to talk about a function being connected and how the points on the graph are connected.